In this video, we're going to tackle the esters, right? So we've looked at reactions of the more reactive carboxylic acid derivatives, and now we're going to approach the ester, right? We've got an OR group next to our carbonyl. We're going to have one section on preparation, and then we will look at reactions of the esters. Now, for this group, there are going to be, I believe, 2 preparation reactions. We're going to see one done under basic conditions and one done under acidic conditions. The first one we see is really just an SN2 reaction that starts with a carboxylic acid, right? If I break down what's going on here, right, if I treat this with sodium hydroxide, all that's happening is we're deprotonating that carboxylic acid, and you're getting an A+ and some water. This is a good nucleophile for your SN2 reaction, so we're just putting in a substrate here, and there's no reason that it has to be a methyl, right? It could be any old R group well, not any old R group. It's an SN2 reaction. You don't want it to be tertiary, but any other R group and a good leaving group, right? Chlorine, bromine, iodine work really well. This is going to give you your ester, right? So you could see this written out in 2 steps like I've done, written out here as a multi-step. It's a 1 and then a 2. Very straightforward. I'm not going to ask you to do this mechanism, but these are steps you have seen before. Under acidic conditions is called Fischer esterification. All right, so this is basic, right? And then we have Fischer esterification. There's the rest of the word. This is going to be acidic conditions. Our lab where we made esters, or where you virtually made esters, used Fischer esterification. You're still starting with a carboxylic acid, and instead of an alkyl halide, you are using an alcohol, right? You have an acid catalyst here. In the lab that we looked at, sulfuric acid was used. And in this scenario, the oxygen right here in the ester actually comes from the alcohol, right? This oxygen here is this oxygen. We are going to go ahead and take a look at this mechanism together. All right, you have it spelled out on the Klein slide, but I'm going to rewrite it as I talk. You start off with your carboxylic acid. It's not nearly as reactive as your acid chloride or your anhydride, so the alcohol isn't going to attack on its own, right, that weak nucleophile. So first what you're going to see is protonation, right? That's going to make that carbonyl a stronger electrophile. You could use H+, you could use HA, you could use protonated alcohol over here. That's likely what you're going to see in a strong acid, kind of like hydronium if it was in water. Just as long as you're pulling it from something that exists, you're not taking it from methanol and creating a strong base, you're good. All right, so we wind up with that protonated carbonyl, much more attractive to, to whatever alcohol it is that we're using. And now that alcohol can attack, we're going to make our tetrahedral intermediate. Come down here. We have OH, OH, and then RO, R, and there's still a proton there, right? There's 2 R groups. Now, from here, we are going to do some solvent-mediated proton transfers, right? We want one of our OHs to leave, and so we're going to show either HA and A-, or you can show it with the alcohol. It would probably be good if I would be consistent here and just keep calling this ROH. There we go. The alcohol can pick up that proton, right? Then we have our neutral intermediate where we have 2 alcohols and an OR group. From here, right, now that we used our acid, we regenerated our acid, now we can protonate one of those OHs, making it into a better leaving group. Now, you might ask, well, why does the OH pick up the proton and not the methanol? Well, or not the OR group? Well, you notice it might. All of these are equilibrium arrows. We're trying to show this reaction going forward. All right. So there we go. Now, once we've made that OH into a better leaving group, we are going to reform our carbonyl and kick off our water. Okay, that's not what I wanted to do. There we go. From here, we are just one step away, right? We have reformed a carbonyl bond. There's still a proton. Don't just lose atoms. And we have our OR. So in that final step, because this is this is a acid catalyzed reaction, we are going to get that acid back. So if you were using HA, this is where you'd use A minus. You can, of course, use your alcohol. If you are using a specific R group, use the specific R groups. Don't write in a generic R. This is a mechanism that you will be responsible for, right? It's several proton transfers surrounding that nucleophilic attack and loss of a leaving group. Those are your 2 preparations of esters. We are going to, okay. So review here, other ways you can make esters. The alcoholysis reaction that we learned earlier in this chapter, where you can take an alcohol and replace a chlorine or the leaving group in an anhydride, that will also leave you with an ester. Right, we just learned that one, so that should be just a quick review right there. Now, reactions of esters. Once we have our ester, what can we do with it? Well, if we want to hydrolyze, we can do something called saponification. Right? This is saponification. This is the basic conditions for hydrolysis. All right, so hydrolysis, but basic. This is taking any ester here, and in the first step, you're treating it with sodium hydroxide. That's what's actually going to replace the OR with an OH. But if you are in basic conditions, it will be deprotonated. So this one will have to be worked up with acid. And that is just to make sure that this proton is in place. This is a very simple mechanism here, right? If we break this down, hydroxide is a much stronger nucleophile than like water or alcohol was, so it can just attack on its own. Open up, you get your tetrahedral intermediate. Are you tired of me saying those words yet? No? Good. OH. Here we go. Now, since we are in basic conditions, it's okay to lose something that's not as good of a leaving group. The OR can leave because the pH is high. It's okay that we are going to create OR minus. We're already in a condition where there is OH minus. So this, when you're in basic conditions, the rules are a little bit different. And there's your product. I'd be happy if we stopped here, but in reality, right, we have that strong base. You are going to deprotonate your carboxylic acid. That's actually what keeps this reaction moving forward. Because you have that proton, you can get stuck at this resonance stabilized carboxylate ion. Esters can also be hydrolyzed under acidic conditions. I'm not going to show the mechanism because we've already done this. The hydrolysis mechanism under acidic conditions is exactly the same as the hydrolysis reaction with acid halides, with one key difference. And I am going to show you the first step. And I think, so this is acidic conditions. I think this would be an excellent opportunity for you in your notes to complete this mechanism on your own. The first step, right, when we hydrolyzed an acid halide, we didn't need acid, we just needed water because it was so reactive. Well, an ester isn't as reactive, so you do have to protonate it first. And that's going to make it a better electrophile, right, for your water to be able to attack. So from here, you should be able to finish that mechanism for hydrolysis of an ester, right? So make sure that you go through and you do this yourself. And also, just a note here, it really is just the reverse of Fischer esterification. So since we just went through that a few slides back, you can refer to that as you try to move forward here. Or, you know, here's a picture of it. Okay, so we can still do hydrolysis. This is jumping straight to aminolysis. I'm going to also add in here, alcoholysis is possible, as is aminolysis. All right, let's address the alcoholysis really quickly. It would be taking one ester and replacing the R group with something else, right? You could still use ROH. It would need an acid catalyst here. Same reason hydrolysis did. It's called a trans-esterification. You may see that pop up in your homework. It's going to follow the exact same mechanism as hydrolysis, except you have an alcohol instead of water. Aminolysis does not need the acid catalyst because, well, the amine is a good nucleophile, right? Whether you're using ammonia, a primary or secondary amine, it will be able to attack on its own, right? So you are still going to be replacing your Z group with whatever your nucleophile is minus one of the hydrogens, right? We saw this in all of the alcoholysis and aminolysis reactions we did in the previous video. I'm not going to go through the mechanism here. It's exactly the same as aminolysis in the previous lecture. It's also a limited it also has limited utility because it's just pretty slow. And that just comes down to esters not being as reactive. Reductions, again, you don't need to know the mechanism. I have not asked you to do the mechanism of a reduction so far, but you just need to, this is just review, be aware that your esters can only be reduced with lithium aluminum hydride and water, and that is going to take them all the way down to a primary alcohol, right? And it's excess LAH because you do have to add it twice. But again, I mentioned this in the last video. Assume that you have enough here. If you don't have enough, it's just going to be a mess. It's not going to give you different products. You do, in this case, get 2 alcohols because this is also released. And then once you add, once you work it up, it will be protonated. And so you wind up with 2 alcohol products here. It's an interesting mechanism. You're not going to be required to know it. You can do a partial reduction, right? So that's your full reduction. Your partial reduction, it's very similar to what we saw with acid halides. but it's with a slightly different reagent. It's still going to be a substituted aluminum compound. It's just not a lithium aluminum compound. And this is called dibol or diba. I think when I was in college it was dibol, but that's okay. It's going to be worked up with water, just like any of our other aluminum reactions. And this is how you can stop at an aldehyde, right? Partial. It's not going to go all the way to the alcohol with an ester. So very similar to what we saw in the previous slides, but a slightly different reagent here, right? A slightly different aluminum reagent. Grignards. This is also just review. I'm not going to show the mechanism of this because I've done Grignard mechanisms so many times. You are responsible for the Grignard mechanism. You are responsible for it with aldehydes and ketones. You will be responsible for it with acid halides, acid anhydrides, and esters. Right? It is important that you use an excess because you are adding it twice, but don't get hung up on that. I'm not going to try to trick you with quantity. What is important to remember is that you get an alcohol and then the R group adds 2 times. Right? That's why you need more than one equivalent. No. The mechanism. I am going to ask you a Grignard mechanism. It's just too important and comes up too many times to ignore it.